Okay, in today's lecture, we're going to cover the first part of the section 11.4 material on tangent lines and derivatives. So in this section, we're going to discuss in more detail the concept of an instantaneous rate of change that we had seen in section 11.3. So let's start with a geometric problem. This question is one of two questions that led to the development of all of calculus. So here was the question of interest. Let's consider a curve C, which is the graph of some function, y equals f of x. And the question is, what is the slope of the tangent line to the curve C at the point where x is equal to a? So let's consider our problem geometrically here. Suppose that we have in the xy plane the graph of some nice smooth continuous function, say y equals f of x. This is defining our curve C in the xy plane. And I'm choosing a value of x, let's say x equals a. So I can find a point on the graph of my function, or this curve C, which would be the point a, and the y-coordinate, since it lies on the graph of the function f, is f of a. Now, we had discussed sort of informally in the last section the idea of a tangent line to this curve as being the line passing through that point, which is increasing at sort of the same rate at which our function f is increasing at that point. So this is what we are calling a tangent line. And the question of interest is, what is the slope of that blue tangent line to our curve at this point? So in the previous section, we saw that we could try to come up with an expression for this slope as the instantaneous rate of change of our function at that point. And it's defined as a limit of an average rate of change. So in order to find our slope, the idea is the following. Let's consider that point on our curve, a, f of a, and then let's choose another point on our curve whose x value is, say, a little bit to the right of a. Let's call it a plus h. We've moved a little bit to the right by, say, by h units. Now, the corresponding point for that x value on our curve would be the point a plus h, and since this lies on the graph of our function, its y-coordinate would be f of a plus h. Now, I know how to find the slope of a line through those 2 points. That is the slope of this red line. So here, the slope of that line would be given by f of a plus h minus f of a, so that is the difference in the y values for those 2 points, over a plus h minus a, the difference in the x values for those 2 points. So in our denominator, we see, well, this a and minus a term cancel, and we're left with f of a plus h minus f of a over h. So this red line, which we're using, which represents an average rate of change of the function from a to a plus h, is sometimes called a secant line. And the slope of our secant line, we found, is given by this difference quotient, f of a plus h minus f of a all over h. Now, to get the slope of our blue tangent line, As we saw in the previous section, the idea is to take the average rate of change, or the slope of this secant line, as these 2 points get closer to each other, or as the distance between A and A plus H, which we were calling H, is shrinking to 0. So as I move these 2 points closer to each other by taking the value of H smaller and smaller, I see that the slope of this secant line, shown in red, starts to become a good approximation for the slope of our blue tangent line. Therefore, the slope of the tangent line will be defined as the limit of the slope of our secant line, which was f of a plus h minus f of a all over h, as h approaches 0, provided that that limit exists. So here, the slope of our tangent line is the instantaneous rate of change of our function at x equals a. It's defined in terms of the same limit that we were looking at in our previous section. So formally, we've sort of informally been discussing what a tangent line is. So formally, what is a tangent line? Well, the tangent line to the graph of a function y equals f of x at a point A, f of a, is the line which passes through that point and whose slope is given by the limit of the slope of the secant line, or the average rate of change of the function f from a to a plus h, provided that that limit exists. Now, if this limit does not exist, there are some examples which we will consider in just a moment, then there is no tangent line to the curve at the indicated point. So this slope of a tangent line, or an instantaneous rate of change, which we've been discussing so far, is given a special name in calculus. It is known as the derivative of a function. So let's define our derivative. We would say the derivative of a function f of x at x equals a is this limit as h approaches 0 of f of a plus h minus f of a all over h, and this limit is denoted as follows. So the derivative of a function f of x at x equals a is denoted as f prime. So it's f with a little apostrophe by it, and this is called f prime, and we're evaluating it at x equals a. So the derivative is defined as this limit, provided that that limit exists. And if this limit does exist, the function f that we're working with is said to be differentiable at x equals a. So it has a tangent line defined at x equals a, is what we mean by a function being differentiable. So let's consider, before we look at some more examples of calculating derivatives, when a derivative exists. That is, when a function may or may not be differentiable. So in our first example, we are asked to determine whether the function f of x, which is the absolute value of x, is differentiable at x equals 0. So let's think about this limiting value. We are looking at whether or not we can define f prime, that is the derivative of f, when x is equal to 0. Now, by definition, this is the limit as h approaches 0 of our function f of 0 plus h minus f of 0 all over h. So let's see what we have here. That is the limit as h approaches 0 of, well, f of 0 plus h is just f of h, and our function was the absolute value function. So we're looking at the absolute value of h minus f of 0. Now here, f of 0, that is the absolute value of 0, would be 0. So we have the absolute value of h minus 0, or just the absolute value of h for our numerator. And then we're dividing by h. So let's recall how the absolute value of h was defined here. So a little scratch work above. Recall that the absolute value of h is actually a piecewise defined function. It's h if h is non-negative. So if you're taking the absolute value of any non-negative number, you get exactly that same number. However, if h is less than 0, if you have a negative number, to get the absolute value, you would take the negative of h. So the negative of that negative number would give you the absolute value of that number. So the function that we're looking at here, the absolute value of h divided by h, well, if we take this definition for the absolute value of h that we were just looking at, and we divide through each part of our definition by h, we would have the absolute value of h divided by h being defined as 1 or negative 1 if h is non-negative or if h is negative. So we're interested in the limiting value of this function as h approaches 0. Now, because of the definition of our function, well, we see it changes its definition at h equals 0. So when we're talking about a limit, we have to consider a left or a right-hand limit here, since our function is defined differently depending on whether h is positive or negative. So if we consider a left-hand limit of the absolute value of h over h, well, if we're approaching 0 from the left, that means we're working with negative values of h. So we would have the limit as h approaches 0 from the left of negative 1. Recall, if h is less than 0, this function is defined as negative 1. And therefore, the limit of this constant value would be negative 1. However, if the limit is being considered from the right-hand side, the absolute value of h over h, if h is greater than 0, is defined as 1. So we would have a limit of 1, which is not equal to the left-hand limit. So this two-sided limit that we're interested in to define our derivative does not exist. We could say D and E does not exist because the left and right hand limits are not equal. So by the one-sided limit theorem, we see if those left and right hand limits are not equal, then the two-sided limit does not exist. So if this limit does not exist, that means that our function f of x, which was the absolute value of x, is not differentiable at x equals 0. Now, a more intuitive idea for this example would be to consider the graph of the absolute value function. So a little more scratch work up at the top here. Let me fit this in. If we are considering the graph of the absolute value of x, well, based off the definition, the absolute value of x is just x, if x is positive, so we have a line through the origin of slope 1 shown here, and if x is negative, we have negative x. That is a line of slope -1 passing through the origin. So the graph of the absolute value function is sort of this V-shaped curve with its vertex or bottoming out at the origin, 0, 0. So we see that for values of x that are less than 0, so as we're approaching 0 from this left-hand side, the slope of this blue line is -1. So the slope of our tangent line would be -1. However, when x is positive, the slope of this red line is +1. So as we're approaching 0 from the right, we have a different limiting value. And so at 0, we don't know how to define the slope of the tangent line. Should it be +1 or -1 or something else? Well, here it can't be defined, so we would have our function not being differentiable at that point. And we see from our graph here that we have a corner in the graph of our function at that point where it is not differentiable. That is sort of a sharp corner where we are rapidly changing the slope of this line. So that corner concept will come into play shortly. Now, related to the idea of a function being differentiable is its continuity. So we have a theorem that says if f is a differentiable function at x equals a, that is, if its derivative exists at a, then f must also be continuous at a. Now, the converse of that theorem says, well, if if a function f would not be continuous at x equals a, then it cannot be differentiable at a. Because if a function is differentiable at a, it must be continuous there. So if we know it's not continuous, then it cannot be differentiable at that point. So we're seeing a couple of cases in these two examples where a function might fail to be differentiable. Now altogether, there are 3 ways in which a function f can fail to be differentiable at a point. The first way is if the graph of our function has a corner at x equals a. So something similar to what we saw for the absolute value function. If we have a corner in the graph of our function at a point, then our function is not differentiable at that point. In part 2, or the second case where we might have a function failing to be differentiable, is if the graph of our function f of x is discontinuous at a. This theorem that we just looked at said, well, if a function is not continuous at a point, then it cannot be differentiable at that point. And the third way in which a function can fail to be differentiable is if the graph of our function has a vertical tangent line at x equals a. So remember, the derivative is the slope of a tangent line to a curve. So if we have a vertical tangent, well, the slope of a vertical line is undefined. So to illustrate those 3 types of functions which would not be differentiable, we could have a function which has a corner, so some sharp corner in the graph of our function, such as this one, or the absolute value of x. If we have a discontinuity, so say if our function makes a jump or has some sort of discontinuity at a point, it is not differentiable there. Or if our function at some point becomes infinitely steep, such that our tangent line becomes vertical, then we would not have a differentiable function at that point. So now that we've discussed these different types of ways for a function to not be differentiable, let's look at an example. So here we are given the graph of a function f below, and we are told to state with reasons the values of x at which the function f is not differentiable. So let's look at them from left to right here. So moving from left to right along our x-axis, the first value where we see that we might not have differentiability would be at x equals, looks like -1 here, since we have a corner. So the first value of x where this is not differentiable would be at x equals -1, because we have a corner in the graph of our function. Now, as we continue to move from left to right along our x-axis, everything looks good until we approach the value 4. We see at x equals 4, our function has a discontinuity. It makes a jump in its definition. Therefore, our function is not differentiable at x equals 4 because it has this discontinuity. Now again, as we continue to travel along the x-axis, everything appears to be fine until we get to this point where x is equal to 8, and it looks like we have another corner in the graph of our function. So at x equals 8, this function is not differentiable because of that corner. And moving forward from x equals 8, everything appears to be fine until we reach this value where x equals 11. It appears that our curve becomes vertical, or has a vertical tangent at this value. So at x equals 11, this function is not differentiable because we have a vertical tangent. So by looking at the graph of a function, we can determine points where it is not differentiable if it has a corner, a vertical tangent, or a discontinuity at some point. So in this next one, we are considering a function y equals the absolute value of x squared minus 4, and we're asked to sketch the graph of that function, and then using that graph determine the values of x at which that function is not differentiable. So to sketch the absolute value of a function, there's a few ways we could do it. Sort of an easy approach is to first ignore the absolute value. So if I were to just consider the function that's inside of the absolute value, that is y equals x squared minus 4, well, this is a quadratic function with a positive x squared value. So its graph is a parabola opening upwards. And we see that it's written in the standard form for a parabola. So we can see immediately that its vertex would be at the point 0, -4. So we have this parabola passing through 0, -4 and opening upward. And we can find its x-intercepts by setting y equal to 0. So we would have x squared is equal to 4, or x would be plus or minus 2 for these points where it's crossing the horizontal. Now, how do we get the graph of the absolute value of that function? Well, let's think about what the absolute value does. It takes any number which is negative and makes it positive. So geometrically, any part of my graph which falls below the x-axis, these are negative values for y, they would become positive y values. So let's think about that. So here, the part of my graph which lies below the x-axis, when I take the absolute value, is reflected above the x-axis, and any part of my graph which was already positive, so anything that was already above the x-axis, will remain above the x-axis. It looks exactly the same. So this would be a rough sketch for the graph of y equals the absolute value of x squared minus 4, where this point is now 0, positive 4, and our x-intercepts are still the same, positive and negative 2. So looking at the graph of this function, we see, well, it appears to have corners at the points x equals positive 2 and negative 2. So it is not differentiable at x equals plus or minus 2. So these were the values of x that we were asked for in the problem. Okay, so in this first part of our section, we've considered the concept of the slope of a tangent line, which is defined in terms of this limit of a difference quotient, and it's called the derivative of a function. And we had looked at some examples in the last section of finding the derivative of a function at a particular point. And we've seen some examples where a function may not be differentiable, namely if it has a corner, a discontinuity, or a vertical tangent at some value.